In this video, we're going to talk about an integral formula for not necessarily a measure of size like area or volume, but we're going to talk about length. So we have this almost like a one-dimensional measure of size, right? We have a two-dimensional measure of size for area and a three-dimensional measure of size for volume. So now we just want to talk about length. So we're going to talk about an integral formula for arc length of some function. First, we're going to remind ourselves about two situations where we are already able to do some arc length calculations. Then, we're going to talk about that slice and sum method that we've been talking about. We're going to hopefully build a Riemann sum and get an integral formula out of it. And then we'll take a look at some examples where we actually do find the length of a curve on some integral using that integral formula that we build. So it seems like kind of a short list of things to do, but it might take a little bit to get through here, so let's get moving. So first, just a quick recap. There's two spots that we see arc length. Just as a reminder, arc length is literally just the length of some curve between 2 points. So first, we've seen this in circles. If you've taken some trig, or if you saw some of this stuff in high school, you know that there's some nice formulas for getting the length of the curvature of a circle between 2 points. And we have this nice formula where we sometimes represent arc length with s, and we just call it r theta, where r is the radius of the circle, and theta is this angle right here, measured in radians. The nice definition of a radian is that it basically gives us this arc length formula for free. So maybe this is something that you remember. This works for nice circular shapes like this. Then we obviously have the straight line. We can find the length of a straight line between 2 points. And this just comes from the distance formula, which is really just the Pythagorean theorem, right? We have this delta x right here. Maybe I'll do this in blue. And a delta y right here, where delta x is literally just the difference of the x values. So that's right here. And delta y is literally just the difference in the y values. And the Pythagorean theorem says that delta x squared plus delta y squared is going to equal d squared. Since this distance has to be positive, we can just look at the positive version of the square root. And this is the distance formula. No big deal. So both of these situations are relatively easy to measure the length between 2 points. What we're going to notice, though, is that when we end up with actual curved functions, we have a bit more of a tricky situation going on. So we're going to use this slice and sum method, where we're going to cut our curved function up into a bunch of different pieces, and we're going to approximate the length of the curve on each of those intervals. Just like with area, we approximated the area by pretending our function was constant on these subintervals, and so we looked at rectangles. Or maybe we approximated volumes by using disks or washers or shells, and then we add up all those volumes. Here, we're going to approximate the length. So when we talk about the arc length of a curved function, we have to figure out which of those two situations that we know we're going to use. Are we going to approximate every interval of our function using a curved arc length like a circle or a straight arc length like a line? It might be tempting to use a circle because functions are sometimes curvy, and so circles are curvy too. And so maybe the approximations will be pretty good. But if we go back to this, you'll notice, we'd have to know the angles in between here, and that could be really tricky. So what we're going to do is use the straight lines. So we're going to take some function, and we're going to connect all of these little dots in our subintervals here, and we're going to use straight lines to represent those. And we could say, hey, if we added up all these red lines, the lengths of all these red lines, that would be an approximation of the length of our green function in between these 2 points, from x equals a to x equals b. So what we need to do is to figure out how to find the arc length of the kth subinterval. Then we'll approximate the total arc length by adding them all up, and then we'll apply a limit, and that'll give us an integral. So we need to first start with just looking at one of these sections and finding the arc length of that. So we'll zoom in, and I've just got a bunch of things labeled now. So we're going to approximate this little L right here. Well, we're not going to approximate that, sorry. We're going to find the length of this L right here, and that's going to approximate the length of our curve, the green function. I've got our coordinates of our points. This is the kth rectangle, so it's going to start at x sub k minus 1 because we start at x sub 0 and then go up to x sub 1 and all this kind of stuff. Basically, the rightmost edge of each subinterval is the index. And so this is the kth subinterval because we have this k index here. Notice this is just the distance formula. We've got a right angle right here, so we can use our Pythagorean theorem. And so we can say L is going to be, maybe I'll say L squared is going to be delta x squared plus delta y sub k squared. We can throw the absolute values on here if you want. We don't really need them since we're squaring things. The absolute value is not actually really necessary here because we could have a negative y value. We'd have to figure out what that means for our triangle, right? Our triangle wouldn't really work because triangles are supposed to have positive side lengths, but we could probably understand what that means. Anyways, this is going to give us our nice little formula for length. It's going to be the square root of delta x squared plus delta y sub k squared. And I'll throw the absolute values on for now because I think I left them in there on later notes, just so it's not confusing that we bounce back and forth. So this is this length L here. Now really, this is L sub k, right? Because this is really the length of just that kth line segment. So now what we're going to do is we're going to build our Riemann sum by adding all that stuff up to see if we can get a decent little approximation of what we have. So it seems like we're pretty much done, right? We just have to apply a limit to this thing and it should turn out to be an integral. But we've got a problem. So we have to sit and look at this and try and figure out why this is going to be an issue. The problem that we're running into is that this is not a Riemann sum. Meaning, when we apply a limit, it's not going to turn into a nice integral form, and we can start to see a little bit about why. There are two things that we're going to run into here, two problems that we have. So, just as a reminder, this is what we've got. Here's our sum, and here's the Riemann sum, and we want to look and see the differences. There are two issues. First is that a Riemann sum has to have a function that takes in an x value that's just some x value from the kth subinterval. That's what x sub k star is. So we have to have a function that takes that in. And you'll notice in our sum, we don't have that. We also need to have this delta x here at the end of our sum getting multiplied, because remember, our delta x is going to turn into our differential when we apply that limit. And so here, our delta x is nested inside of this square root. We don't really have a function here taking in some x value, right? These delta x's and delta y's are both functions of two x values because we're looking at a difference between x values and a difference between function outputs at those x values. So this is a problem. We need to come up with some way of converting this over to a Riemann sum, a function that takes in one x value from our subinterval somewhere, multiply that by delta x. So let's do that. So what I'm going to do is, I probably should have included our summation here. We've got that L is approximately equal to our sum from k equals 1 up to n of the square root of delta x squared plus the absolute value of delta y sub k. Oops, I forgot my delta in here. Cool. What I'm going to do is some factoring. I'm going to pull out a common factor, and you're looking at me thinking, wait a second, there is no common factor. But I'm going to go ahead and do that. So actually what I'm going to do is say, let's just work with L sub k. That way I don't have to worry about that sum, and I don't have to worry about the approximation. So I'm just going to look at that one little length. So I'm going to factor out delta x squared, but I'm going to leave it under my square root for now. So now I'm left with a 1 plus delta y sub k squared in absolute values over delta x squared. This is kind of weird looking, but you can go ahead and just multiply this back in to double check and make sure that this works. If you multiply it back in, you've got delta x squared plus delta y sub k squared in absolute values. That's all fine. Now what I'm going to do is notice I've got a product of things underneath my square root. I'll split my square roots up. So here's my delta y sub k squared over delta x squared. Notice that this part then is a square root of a perfect square. So this is going to be delta x. We should be careful. It's technically the absolute value of delta x, but delta x is already positive, so we don't really need the absolute values here. Multiplied by 1 plus, and then I'm going to do this. I'm going to say this is really this fraction squared. I'm going to not worry about the absolute values anymore because, again, when we square it, it becomes positive anyway, so who cares if delta y is negative? Cool. If you would like, I can rewrite this one more time where I just move this delta x to the very end. That looks better. Now we've got that our total length is approximated by the sum from k equals 1 up to n of this. I'm not going to rewrite it out. I'm getting smart with this technology. I'm just going to copy, paste, bang. That is a little bit closer to a Riemann sum, right? We've solved one problem. We pulled delta x out to the end. Notice we still don't have a function that takes in a single x value, so that can be kind of tricky, but we do have something going on right here. This delta y sub k over delta x, we should think about what that actually is. We've seen this formula before. Change in the y variable on that subinterval over the change in the x variable on that subinterval. If we think about these 2 points that we had, and we were connecting the dots, delta y over delta x, that's just really the slope between the ending points. Of our subinterval. That's going to be helpful for us. So what we should do is try and convert this slope into something else. And I want to remind us about the mean value theorem. The mean value theorem is super dope. It's going to be really helpful for us. So a reminder from Calc 1. If you've got a function that's continuous on the closed interval and differentiable on the open interval, then there exists some sort of an x value, we'll call it c, in the open interval between a and b, such that the derivative f prime of c is equal to this quantity f of b minus f of a over b minus a. All right, well, what is this saying? What this says is that the slope between ending points is equal to the derivative somewhere in the interval. Oops, let me fix this. There we go. So we have our slope between the ending points. We want to come up with a function output of some single point in the interval, and we can use the mean value theorem for this. So what we're going to do is pick that c value, that point that satisfies the mean value theorem, to be the point where that average slope is equal to the instantaneous slope. Then we can swap that out. So we're just going to take this average slope here and swap it out for the instantaneous slope at x sub k star. Now, x sub k star is not representing some random x value. It's representing a specific one. It's the one that's guaranteed to exist by the mean value theorem. So we're just going to be clever with how we pick that thing. Then, once we've done that, we have that L is approximately equal to this sum of a function output with one input times delta x. This is a Riemann sum. So what we can do is do our slice and sum method. The kth subinterval, the length on that is equal to the square root of 1 plus the derivative at x sub k star squared times delta x, all under a square root, sorry, and then multiplied by delta x. That means the total length is approximated by the sum of all those little lengths, and that means the total length is exactly equal to the limit as n goes to infinity of this sum, and that is an integral from a to b of the square root of 1 plus f prime of x. Remember, our x sub k stars just turn into x. Essentially, when all those subintervals get tiny, 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 tiny in width, the point guaranteed to exist by the mean value theorem is the single x value in that subinterval, which is kind of a weird thing to think about. And then our delta x turns into a differential dx. So this is our arc length formula. So as long as f has a continuous first derivative, now this is a little bit different. Earlier, we just needed the derivative to exist, right? We needed our function to be differentiable on the open interval because that means that we could use the mean value theorem. Now we need this thing to be continuous, the derivative to be continuous, and that's so that it's actually integrable. So technically a little bit stronger of a condition, a little bit harsher, I should say, of a condition, but oh well. Then the length of the curve between those two ending points is going to be the integral from a to b of the square root of 1 plus the derivative of f squared times dx, which is our delta x, but we really aren't thinking of that as multiplication. We're thinking of that more as just a notational ending point of our interval. Something that we should note is that this is kind of ugly, right? We have all this stuff under a square root. We have some composition going on here. So it might not make it easy to integrate this thing, which is no big deal. In a lot of these, we can just get by setting up some integrals and then saying, all right, as we learn more integration methods, we'll be able to figure these things out later. For now, I'll take a look at some examples that we actually will be able to integrate and get all the way through. And we'll be able to evaluate these arc lengths. But it's not a big deal if we just have to kind of leave ourselves with setting up the integral, putting it into this nice form, simplifying whatever we can, and then once we get to the spot where we would normally find an antiderivative, we can just stop for some of these. Because for some of them, we still have to build up some integration methods to know how to do this. All right, so here's some examples. Let's find the length of the function. X to the 3/2 on the interval from 0 to 4. We'll remember our arc length formula. It's going to be the integral from, I'll say, a to b of the square root of 1 plus the derivative squared dx. So we're clearly going to need the derivative of this function. That's going to be 3/2 x to the 3/2 minus 1. That's going to be 1/2. All right, so let's go ahead and put all this in place. This means L is going to be the integral from 0 to 4 of the square root of 1 plus 3/2 x to the 1/2 squared dx. When we square this thing, we're going to have that 3/2 squared, so that's 9/4, and then we'll have the x to the 1/2 squared, which is going to be the absolute value of x, but notice x is only taking on positive values anyways, so we can just say x. And then for something like this, oops, there we go, we'd have to integrate, and that's not a huge deal. We can use a quick little u substitution. Hopefully we remember how that stuff goes. du then is 9/4 dx, so I would normally go ahead and put my 9/4 out here and then a 4/9 there, and then I can take this part and wrap that up as du, and all the stuff under the square root becomes u, and our new integral is 4/9. I'm going to go ahead and take these limits of integration and plug them in as well. So my new limit of integration on the bottom is 1 plus 9/4 times 0, so that's just 1. And then I have 1 plus 9/4 times 4, that's 1 plus 9, so that's 10. And then I've got a square root of u, I'll call that u to the half, du. Add 1 to my exponent, divide by that value, 4/9 times 2 times u to the, oops, not 2. Adding 1, so this is 3/2, so then I have a 2/3. There we go. Evaluate that from 1 to 10. I can multiply as much as I want through here. Everything should work out pretty well, and you should be able to figure this thing out. So let's see. 4/9 times 2/3, what's that going to be? That's going to be 8/27. And then I've got 10 to the 3/2. Which I don't really know what that is, and frankly, I kind of don't care. And then I've got that same thing, but it's 1 to the 3/2, so minus 8/27. Cool. You could probably simplify this a little bit nicer, rewrite this a little bit better. I don't really care, though. Maybe I'll factor at least, and we'll call it that. That's our arc length of that function. Neat. Here's another one. What I want you to do is to see if we can get this thing set up. R here is going to be a fixed value. It's not variable. Note that this is the formula for like a circle. Maybe I'll draw it first, and then I'll let you start things out. So what this function is this. It's a half circle. And so we've got a negative r here and a positive r here. And so what we're looking for is this length. And notice that that's really like a circumference kind of thing of a quarter circle. It's the arc length, at least, of a quarter circle. And so if we multiply our answer by 4, we should be able to get the general circumference formula. We know that circumference is 2 pi r. So our arc length better be like 2 pi r over 4 or pi r over 2. So we'll see what happens there. Pause the video, see if you can get things going, and that should be good. All right, so hopefully we've caught up a little bit. Take a second and follow through if you want what I'm doing here. But once you plug everything in, you just have to do a little bit of algebra to kind of rewrite this in a nice way. It's kind of ugly, but if you combine fractions and then notice that you can square root the top and pull it right out and factor it, we end up with this nice form where when we anti-differentiate this, this is just sine inverse of x over r, and then we can evaluate it from r, or from 0 to r, sorry. So this is, I'll put it down here, r sine inverse of r over r, that's 1, minus r sine inverse of 0. Sine inverse of 0 is 0, so we really just have r sine inverse of r, and you might remember that, or sorry, sine inverse of 1, there we go, and you might remember that sine inverse of 1 is pi over 2. So we have pi r over 2, which clearly when you multiply that by 4, you end up with 2 pi r. So this is the arc length of a quarter circle. All right. Hopefully that's enough to get you started on all this stuff. Again, there are a bunch of these where the functions that you get aren't really that nice to work with, and so once you find the derivative and put it into this form, it still might not actually end up with a workable integral that for now we can actually anti-differentiate. We'll build up a lot of our strategies later on in this course, and so maybe later we'll be able to come back to some of these arc length integrals that were hard for us now, and we'll be able to do them later. But for now, I mostly just care about getting these things set up, understanding how the mean value theorem comes into play, and why that adds some new requirements on about the derivative having to exist and be continuous. That's a new thing for us. So hopefully we can see how this slice and sum strategy is able to give us this nice integral formula.